A single docked container ship can burn through 15 tons of fuel a day without moving an inch. Across the world's ports, that adds up to millions of tons every year, burned by ships that are, for all practical purposes, parked. But ship crews aren't doing this out of laziness. So, what is actually stopping them from simply flipping a switch? The answer involves fuel that turns solid below a certain temperature, a global patchwork of incompatible port power grids, an emergency readiness rule buried in international maritime law, and an industry that spent decades choosing the lesser of two very expensive problems. At the heart of the world's largest cargo vessels are massive, low-speed two-stroke crosshead engines. Designed by industry giants like MAN Energy Solutions, WinGD, and Wärtsilä, these colossal power plants are built for unrelenting reliability rather than convenience. They do not operate on the refined water-thin diesel used in road transport. Instead, they run on heavy fuel oil, or HFO, the thick, viscous residue left at the bottom of the refining column after lighter fuels are distilled. At room temperature, HFO has the consistency of cold peanut butter. With a kinematic viscosity exceeding 180 centistokes at 50 degrees Celsius, the fuel will solidify if its temperature drops just 10 to 15 degrees above the surrounding seawater. To keep up to 3,000 cubic meters of this material pumpable, a ship must run a continuous high-energy heating chain. The oil is maintained at 40 to 45 degrees Celsius in double-bottom storage tanks just to keep it fluid enough to move. It is then pumped into settling tanks heated to between 50 and 80 degrees Celsius, allowing water and heavy sediment to drop out. From there, the fuel passes through high-speed centrifugal purifiers before entering service tanks kept at up to 90 degrees Celsius. Finally, right before injection into the engine cylinders, steam heaters blast the fuel to between 120 and 150 degrees Celsius to achieve the fine mist needed for combustion. If this heating chain is interrupted and the fuel cools, the consequences are immediate and severe. The oil thickens into an unpumpable sludge, clogging fuel lines, choking purifiers, and seizing injection pumps. Reversing this solidification is a grueling multi-hour process of manually flushing lines and using steam tracing to melt the blockage. Keeping the auxiliary engines running at berth provides the constant steam and electrical power required to keep this entire fuel train hot and pressurized. Maintaining this constant flow ensures controlled thermal readiness. But what if reheating the fuel were the only issue? Could they not simply warm it back up each time and start fresh? They could try, but that is only the first reason. The second reason is something that surprises almost everyone who learns about it. Most people assume that when a ship docks, it can simply plug into the local power grid like an electric car. In reality, a large merchant vessel requires an immense continuous electrical supply of up to 10 megawatts to run its onboard systems, cargo cooling units, and pumps. This is equivalent to suddenly plugging an entire small town of several thousand homes into a single dockside socket. Most local municipal grids and individual port berths simply cannot handle this sudden, massive demand. To bridge this gap, the international maritime industry established the IEC IEEE 80005-1 High Voltage Shore Connection Standards. Yet standardized rules do not instantly solve physical mismatches. Global fleets are divided. Many Asian-built ships operate on 60 Hz systems, while European port grids run on 50 Hz. Connecting them directly is impossible without massive, expensive frequency converters. There is also a voltage mismatch, with ships requiring either 6 or 11 kilovolts. Overcoming these hurdles is incredibly expensive. Upgrading a single port berth with the necessary substations and high-voltage cable management systems can cost up to $10 million, while retrofitting an older ship with onboard transformers costs up to $2 million. Where policy and funding align, the investment succeeds. In Oslo, national grants established high-voltage shore power, while in Los Angeles and Long Beach, strict environmental regulations forced the adoption of shoreside power grids. But early Northern European pilots struggled with poor uptime and compatibility errors before these international standards were codified. Ultimately, the vast majority of the world's ports still lack these multi-million-dollar shore connections. Until this infrastructure gap is closed, ships have no choice but to burn fuel at the berth, using their own auxiliary generators to keep food cold, water pumping, and lights on. Now, there is a third reason, and it might be the most critical one of all. This one has nothing to do with fuel chemistry or shore power. It comes down to a standing obligation of maritime law: readiness. Under the International Convention for the Safety of Life at Sea, or SOLAS Chapter 2, 1 in the International Safety Management Code, a vessel must maintain the ability to maneuver in emergencies. Classification societies like DNV and Lloyd's Register expect crews to operate within a tight readiness window, even while tied securely to a concrete berth. In a busy harbor, danger can materialize in minutes. A sudden storm, a dragging anchor from an adjacent vessel, or a nearby fire can force a ship to cast off immediately to avoid disaster. Here's the part that catches people off guard. You cannot simply press a start button on a cold marine engine. Reversing a complete shutdown of a massive 10 to 30 megawatt main engine takes hours. The process is a carefully timed physical sequence. First, the lubricating oil must be heated to at least 35 degrees Celsius and circulated to protect the bearings. Next, jacket water must be warmed to over 50 degrees to prevent thermal shock, which can literally crack the engine block. The heavy fuel oil must be circulated through purifiers and heated to over 120 degrees to ensure proper atomization. Lastly, the massive crankshaft must be slowly turned with auxiliary gear to verify clearance. This entire process takes up to 4 hours. If a ship is in a cold state when an emergency strikes, it is helpless. By keeping the auxiliary engines running, the crew maintains the constant steam, electricity, and pressure needed to keep the primary propulsion system in a state of hot standby. If you want to support more of these maritime documentaries, please take a moment to subscribe. When an operator sits down with a ledger, the math of marine engineering transforms into cold, hard cash. To understand why a ship idles, look at the physical toll of a cold restart. Reheating a 2,450 cubic meter double-bottom fuel tank system on an Aframax class vessel from 15 to 80 degrees Celsius requires roughly 75 megawatts of thermal energy over a 4-hour window. That is the energy equivalent of running a small city's power grid just to melt fuel. Beyond fuel, thermal cycling degrades metal, forcing a cold multi-story engine block to expand and contract repeatedly causes micro-fractures in cylinder liners and stresses heavy bearings. Crews managing these demanding multi-step start sequences face heightened exposure to operator error. Then there is the cargo. Modern container ships carry hundreds of refrigerated container units loaded with perishable foods and pharmaceuticals. A single power interruption can ruin millions of dollars in cargo, triggering massive liability claims from cargo owners and heavy port penalties for blocking the berth. Decades ago, ship operators ran these numbers. The verdict was clear. Keeping auxiliary systems running at berth was a highly calculated defense against catastrophic loss. The economic choice was not even close. But why is this decades-old environmental compromise now beginning to fracture? For decades, the balance sheet favored constant idling because fuel was cheap and environmental costs were externalized. But as global bunker prices climbed, burning 1 to 2 metric tons of fuel daily just to keep a docked ship's lights on became a glaring operational loss, the equivalent of burning thousands of dollars a day while standing still. This financial leak coincided with a massive wave of regulatory and social pressure. the International Maritime Organization introduced MARPOL Annex 6, tightening global limits on sulfur and nitrogen emissions, while local ports established strict regional air quality zones. At the same time, coastal cities expanded, bringing residential neighborhoods right up to the edge of working berths. The continuous low-frequency hum of auxiliary generators and the visible plumes of exhaust soot became immediate public health battles. When a single ship idles, it is a local nuisance. But with tens of thousands of active merchant vessels globally, the cumulative impact of docked emissions became too massive to ignore. The traditional calculus of marine operations began to fall apart under the weight of climate targets, high fuel overhead, and community outrage. So what changed? The response has been a mix of highly targeted engineering solutions. The cleanest option at the berth is shore power. In Europe, the Port of Rotterdam's shore power strategy relies on an ABB system designed to deliver over 100 megavolt amperes of electricity. That is equivalent to running a medium-sized manufacturing district. By keeping auxiliary engines silent at 3 flagship terminals, the port aims to prevent 96,000 tons of carbon dioxide emissions annually. But shore power is not a universal fix. For vessels moving between less developed docks, operators turn to exhaust gas cleaning systems, known as scrubbers. These units wash sulfur from generator exhaust. However, they carry heavy trade-offs. Open-loop scrubbers discharge acidic wash water back into the ocean, prompting several ports to ban them, while closed-loop systems require complex chemical dosing and landside sludge disposal. Alternatively, ship owners are investing in fuel flexibility. Propulsion giants like MAN Energy Solutions and Wärtsilä now supply dual-fuel engines, like the Wärtsilä 34DF. These designs allow vessels to burn liquefied natural gas, methanol, or conventional fuel. Yet, dual-fuel technology is capital-heavy, often adding up to $20 million to the price of a new build. It works well for large container ships making scheduled calls at major ports. But does it solve the problem for a bulk carrier making an unscheduled stop at a smaller port? Not entirely. Even when a port has the correct plugs, the final decision to shut down the engines rests with the ship's crew. For a chief engineer, the pressure to maintain power is absolute. In the maritime world, a blackout is the ultimate failure. A sudden loss of electrical power while docked can freeze cargo cranes, shut down ventilation, and disable ballast pumps, risking vessel stability. If the ship carries hundreds of refrigerated containers loaded with fresh food or pharmaceuticals, even a brief power loss can ruin millions of dollars in cargo. Connecting to an unfamiliar shore power system adds a physical maintenance burden. High-voltage cables, weighing hundreds of pounds, must be manually guided and connected in all weather conditions. The crew must sync the ship's electrical system with the local grid, a delicate changeover process that engineers have seen fail. If a breaker trips or a frequency converter fails during this handoff, the ship goes dark. Marine engineers are judged on reliability rather than experimentation. A chief engineer who burns a few extra tons of fuel to keep auxiliary generators running is playing it safe. An engineer who plugs in and triggers a blackout faces immediate liability, intense schedule delays, and potential career ruin. Can you blame them? For the people operating these massive vessels, the choice is clear. The traditional method of keeping auxiliary engines running is a calculated decision to prioritize safety and continuity. Reliability remains the ultimate law of the sea. This multi-decade timeline is dictated by the sheer lifespan of commercial vessels. A modern merchant ship is built to remain in active service for 20 to 30 years, meaning the engineering decisions made today will shape port operations well into the middle of the century. Unlike consumer vehicles, which cycle through generations in a few years, the global shipping fleet changes at a crawl. This slow turnover ensures that legacy ports and older vessels will coexist with new, low-emission technologies for decades to come. Because of this slow replacement cycle, the industry relies on a layered, incremental transition rather than a sudden fleet-wide overhaul. Operators are increasingly adopting intermediate technologies to bridge the gap. Among the most practical pathways are battery hybrid auxiliary systems. Firms like Corvus Energy have pioneered large-scale lithium-ion battery installations designed for retrofitting existing hulls. These systems operate much like a hybrid car's regenerative braking, storing excess electrical energy during transit and releasing it at the berth. For short port stays, these battery banks can support the ship's entire hotel load, allowing the crew to silence the auxiliary generators completely. Yet, even these hybrid solutions face physical limits. Retrofitting a massive battery room requires dry dock time, significant capital, and structural space that older bulk carriers and tankers simply do not have. How do ship owners justify these investments when the infrastructure ashore remains so uneven? They do so by calculating the long-term survival of their fleets. The path forward is not a single, dramatic shift, but a gradual accumulation of technical compromises. Until the entire global infrastructure aligns, the quiet hum of a running engine remains the price of keeping the world's trade moving. That low hum and faint scent of exhaust drifting across the harbor water is not a sign of neglect. It is the sound of a rational compromise between fuel chemistry, port economics, and uninterrupted power. While shore power grids are beginning to clear the air, this deeply calculated maritime balance persists. The industry is evolving, but the economics remain. Subscribe for more deep dives into global industry.